Hello, this is Devin Guerra, and I'm just going to be taking you through Monte Carlo Lab 5. We're working more on optimization. And so we have three different problems. The first one being to improve our TSP from the previous lab. So I'm not going to go through all of this again, but I will show you the improvements we've made. Prior to last week, there was a single mutation, but in order to improve that, we've added some more through this switch case kind of setup that MATLAB is able to have. But first, in order to perform these mutations, we have to, whoops, sorry, that's not correct. We have to organize our cities into 2x2 matrices that'll be pitted against each other. This is sort of the genetic algorithm kind of tournament style approach. What we'll be doing is we'll be mutating the best row distance to get 3 new routes and form this small matrix of 4 rows. And so the different methods we'll be doing, we'll be switching K. The first method is to flip 2 cities and the cities between. The next is to sort or swap, and then we have a slide or sort. And then the last option is to do nothing. So as our iterations go through, they'll be mutated in order to achieve the best route. And I will show you this problem. And this approach works a lot better for a larger amount of cities. So I'm going to pull up this window and I'll hit run. And so here we can see our minimum best distance is 292.7396. And whoops, I forgot to clear our figure. But this let me run it for you one more time. This is our figure. So as you can see, it's finding those best routes as it is going. And this is sort of a greedy approach. But for our next problem, we'll be handling a genetic algorithm load distance layout. And so we're kind of using a code given to us by our professor and making a modification to that to make it better. So first we initialize all of our variables. We'll initialize our matrices. We'll generate a pop size of permutations for the layout, find the minimum cost of all the trials, and keep the best member. We're going to shuffle the population for a new tournament, subgroup the population into groups of 4, and find the best of the 4, overriding the worst 4 from the subgroup. And then we're going to be going through a mutation, and this is where my addition was made. So originally, like the TSP, we have a flip, a swap, and a slide. But my addition is to create some sort of scramble or shuffle. With basically, it's a random permutation, so you'll get a vector of multiple layouts, and it will just randomly sort all of the elements of this vector, and then otherwise we do nothing. And then we'll insert the best of 4 winner, and then we will basically get our optimal job shop layout. So I'm going to show you that code now. So, well, first I'm going to show you without my addition, and the result we get. So here is my code here. So I'm just going to comment that out. I'm going to run this. We have this chart here outputting our department assignments as well as the minimum cost as the iterations are calculated. And so here we have an answer of 2.5462. And so I'm going to now include my my scramble, and we will show you the result that gets. And then we get an answer of 2.617, which is higher than 2.54. And so finally, what I want to go through with you most importantly is we got to choose our own problem, and so I chose to do a nurse scheduling problem. It's fairly basic, but we are generating nurse data. I will actually go through the pseudocode with you of that. Okay. We start by initializing our nurse information. So we have hours worked, the nurse ID, and their wage, as well as the shift. So we're going to initialize variables, making our best infinity, our number of iterations, and then here's our algorithm where from 1 to the number of iterations, we are going to scramble the nurse ID and matrix rows. So scramble those with random permutations. And then we're going to extract the hours worked from that matrix, as well as the nurse IDs for later calculations and our final schedule. But we're going to initialize our first values for the current, which is the total number of hours worked by nurses, and our total cost. And so we say if the total cost is less than the best, which to start out it should, because we set out our best to be infinity. And then we have our cost function. So for j of 2 to the number of nurses, if our current hours worked by the nurses is greater than the length of the shift, or is less than the length of the shift, excuse me, we'll take our current hours worked and our current cost, and we'll calculate our total cost and total current. And then if our total current is greater than the shift, so let's say it's a 24-hour day, and a worker is scheduled to work longer than that 24 hours into the next shift, I guess, into the next day, we'll calculate overtime, which our overtime is double their wage for those extra hours worked, and then we're going to add that overtime to our total cost, run through the iterations, and with all of these sorted, the scrambled nurse IDs and rows from that, we're going to get our best cost, and then we're going to return our nurse schedule and our nurse minimized best cost. So I'm going to run that for you here. And we see our best is 8917. And this is our schedule. So we'll schedule nurse 14 first, then nurse 1, nurse 6, nurse 19, and so on. And each of the values for the nurse information we randomly generate at the start is listed in this table. But that really concludes this assignment. So thank you for watching.